In this video, we'll talk about the Cauchy Schwarz inequality and the dot product. So both of these things are fundamental to mathematics and much of physics, especially when talking about things like energy and work done. So before I talk about Cauchy Schwarz, let's introduce the dot product. Okay. And I'm going to define it straight up. Let's say I have two vectors, x and y, in R3. Then x can be written in terms of coordinates. Its coordinates with respect to the standard basis, which are just the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it has coordinates with respect to these bases. And let's say it has coordinates x1, x2, x3, and y has coordinates y1, y2, y3. Then the dot product of these two vectors, let's define to be this. So we take each coordinate and multiply it together, and then we sum over all coordinates. So that can also be written like this. Okay. Now, at the moment, I haven't really shown you why this is significant, but that's exactly what I'm going to do now. So we're going to provide an equivalent definition of this dot product. Let's say this is the XYZ plane. So X, Y, Z. And let's take two vectors. So maybe this is vector 1, this is X, and this is vector 2, so Y. In fact, let's say this is vector 3. This looks to be x minus y. Now, just looking at the plane, which contains the vectors x and y, let's take this angle, theta. Okay? So we're just looking at the plane that contains x and y, and therefore also contains x minus y. Now, before we do this, before I explain this equivalent definition of the dot product, there are several things about the dot product with the definition I just presented that are true, and I'll leave those things as an exercise for you to prove, and these are the properties that I'm talking about. So the dot product is distributive, meaning that this is true, also the dot product of the same two vectors is the same thing as the magnitude of that vector squared. Is there anything else that's significant? Oh yeah, the dot product is also commutative. And is there anything else that's important? No, there's nothing else that's really significant. So these are just some properties of the dot product with the current definition that I've provided that are true, which you can check for vectors in R3. And in fact, it even works with vectors in Rn. Anyway, so back to this diagram over here. Let's apply something. So since this is a triangle, we can apply the cosine rule to it. So I'm just going to apply that. Therefore, the magnitude of x minus y squared is equal to the magnitude of x squared plus the magnitude y squared minus twice the magnitudes of x and y multiplied by cosine theta. Now, the magnitude of x minus y squared is really just the same thing as x minus y dot x minus y, which is equal to the magnitude of x squared minus twice the magnitude of x dot y. And I've just forgotten to include a property, which is that any scalar multiplied by x dot y is equal to ax dot y. It's immaterial. The scalar can just essentially be ignored. Plus the magnitude of y squared. That's equal to this stuff here. So we can cancel some x squareds and y squareds, and we begin to see that we have an equivalent definition. X dot y is actually equal to the magnitude of x, y, cosine theta, where theta is the angle between x and y. And in fact, it doesn't even matter if we choose 2 pi minus that angle, because as we know, cosine of 2 pi minus theta, which is equal to cosine of negative theta, is just cosine theta, because cosine's an even function, so it doesn't matter if we choose this angle either. So here is our equivalent definition of the dot product. Now we have two different definitions of this new operation, which I've just introduced. Let's go and prove the Cauchy Schwarz inequality. So what does the Cauchy Schwarz inequality say? Well, here we'll be working in Rn. So earlier I defined x dot y as this summation from I equals 1 to 3 of xi, yi, where xi is the ith coordinate of vector x. We can also just extend that to Rn. So in general, x dot y is just the sum from I equals 1 to n of xi, yi. Now all the properties which I previously mentioned of this dot product still hold in Rn, and that again you can try verifying for yourself. So Cauchy Schwarz inequality. This is a celebrated inequality in mathematics, and it's very important. It's very useful, which we'll begin to actually use it in the next few videos. So let's get to proving it. Basically what the inequality says is if we have vectors x and y in Rn, then the magnitude of the dot product of x and y, remember the dot product of x and y is also a scalar, is actually always less than or equal to the magnitude of x multiplied by the magnitude of y. This multiplication is, again, just scalar multiplication. So we'll prove this, and this is quite a standard proof. You'll be able to find this on the internet. It's not an obscure proof or anything. It's very standard. So let's consider the expression a xa plus b, where x is actually in the reals and a, b are some vectors in Rn. Let's take a dot product. So let's take the dot product of this with itself. Now this is equal to, well, by the distributive law, x squared into the magnitude of a squared plus twice x a dot b plus b magnitude of b squared. And I've just applied all of the properties of the dot product in order to get here. But we also know by another property that this is equal to x a plus b squared, where this is a magnitude. It's the Rn norm. So the norm in R2, so the magnitude of a vector with two coordinates, x, y, the magnitude of that is root x squared plus y squared with 3 coordinates in R3. We can extend that quite naturally. It's just root x squared plus y squared plus z squared. You can imagine that if we have n of these, so a1, a2, an, whoops, I'm getting really messy here. It's just square a1 squared, a square root a1 squared plus a2 squared all the way to an squared. So this is just the norm or the magnitude of a vector in Rn. It makes a bit less sense to call it a magnitude when we're working in Rn because, at least I have a hard time visualizing what R4 looks like, let alone R5 or R6. But anyway, it's sort of like the magnitude. But that's equal to, that's always greater or equal to 0 because it's a square root, right? So in other words, this stuff over here is also greater or equal to 0. Now, interestingly, this looks like a quadratic. It looks like a quadratic in x, which it is because x is a real number. And so if we were to graph that, x, I guess you could call this y, it's always going to be either touching the x-axis or above it, which tells us something about its discriminant. It means its discriminant is less than or equal to 0. Okay? So, what does that mean for this quadratic? Well, let's see. What's b in this case? B is just 2 into a dot b. So that squared is 4 into a dot b squared minus 4. Now a here, in this case, is just a squared. So a squared, and c is just b squared, is always less than or equal to 0. So what that implies is that, just dividing both sides by 4, a dot b squared is less than or equal to the magnitude of a squared, magnitude of b squared. Now a dot b squared is just the same thing as the magnitude of a dot b squared, which is less than or equal to the magnitude of a squared times the magnitude of b squared. And square rooting both sides, since everything here is larger than 0, we're allowed to do that. We have the magnitude of a dot b is less than or equal to magnitude of a times the magnitude of b. So that's a really nice inequality, and it's really useful. You can also rewrite it in a bunch of other ways, just using sort of a summation, and it's commonly expressed as follows. So it's commonly expressed like this as well, and this is how you'll usually see it. Okay, so that's the Cauchy Schwarz inequality. I think that's enough for one video. We've discussed most of the things. Actually, sorry. Before I finish, let's quickly prove something also very important, the triangle inequality. But the triangle inequality in Rn, so for vectors in Rn, not just in R2. The way we'll do this is, let's consider a plus b dot a plus b. I have to hurry up here because it's nearly 15 minutes, and that's the longest my recording software allows me to record for. So we know that this is nothing but the magnitude of a squared plus 2 into a dot b plus the magnitude of b squared, which is certainly less than or equal to the magnitude of a squared plus twice the magnitude of a into the magnitude of b plus the magnitude of b squared. Now, why is this true? Well, by Cauchy Schwarz, we know that a dot b is less than or equal to the magnitude of a dot b, which is less than or equal to the magnitude of a times the magnitude of b. So just applying that here, we get this. Now we can just cancel some stuff. And, oh, whoops. We shouldn't cancel some stuff. My mistake. We get a plus b squared is less than or equal to, well, this stuff here is really just a plus b squared. So square rooting both sides, we get a plus b is less than or equal to a plus b, the magnitude of a plus b. And there's another inequality called the reverse triangle inequality, which looks like this, which you can prove very similarly. Thanks for watching.